for inviting me here. It's a great pleasure to participate in for this conference. It doesn't seem working, I guess. Should I turn it on? Oh, all right. Okay. So I'll be talking about a simple example of a Laplacian growth. So this model has some features of physically interesting models, but it is, of course, well, drastic simplification, and of course, it's much simpler than all the structures discussed in the previous talks. So the model is the following. So we'll be considering deterministic growth well, okay. So eta is a real parameter. Right. Okay. So we'll be considering a family of compact sets K that depend on T, and the growth is localized at finitely many points. So eta is a fixed real parameter, and then the rules are the following: that the arms follow the field lines. So E is the Laplacian field. You can represent it using conformal map. Well, this field is changing all the time. But at any moment, the velocity is proportional to, so the velocity, the curve is second order tangential to the field line at that moment. Second, the velocities are proportional to a fixed power of the field. So of course, it's infinity at the tip, but we have to rescale it. And then, I repeat, eta is a simple, well, is a...
Sorry, could you, so does E of t coincide with the gradient of the electrostatic potential?
Yes, but precisely, right. It's the electrostatic potential. Now, well, two extreme cases, if eta is 0, no matter what configuration we start with, so the blue shape will set. So then eventually the arm will spread out, and in the limit we get as many arms as we started with, and they will be straight lines, well, asymptotically, and at, well, the configuration.
The last slide back or tell us, I've forgotten how does that parameter come in?
Yes, right. Yes, right. So it's just a fixed parameter, and the velocity is proportional to the magnitude of the field at the tip points raised to the power eta, right? So if eta is infinity, then, well, just one arm, the arm with the largest concentration is growing. If eta is 0, then they all grow simultaneously at the same speed. So, yeah, only finite number of arms, 1 million arms. So we start with 1 million arms. And then we want to know what happens at the end.
You have standard DLA.
Well, no. So I think it's the number of arms. Okay, I'll just say, well. Okay, so now if it is infinity, like I said, just one arm will straighten out, and that's it. Now, for intermediate values of eta, we have something in between. And the mechanism is, of course, the main mechanism is the competition between arms. Because the field is, well, in analysis known as harmonic measure, one of the ways to define it is to send a random walker and see, look at the probability to hit the tip of the arm. And so long arms will screen short arms will stop growing, long arm will grow faster. So it's a competition. The questions are, yeah.
So is DLA a special case of this?
No, this is a very, very, very simple, much simpler, yeah, what was way more simple. No, each time I'm going, I follow the field line. I follow the field line as close as possible. But the field is changing at all times. So that's, mathematically that's difficult. So the process is not local. So we need to keep track of the whole evolution of it.
But the process is deterministic. It's not
the process is deterministic, okay. If we add, we can also add, so this process can be, represented by Loewner's equation with n growth points, where n is the number of arms. So then we need to describe the interaction between these points. So the points corresponding to the tips, the points on the circle, they interact according to, this is known as Loewner equation. It's precisely the same. We can add, so that's a drift term. We can add a stochastic term to, like SLE2. And then this is probably what you get if you have n, so if you perform a Laplacian random walk with n growth points. Now, if you add also, if you don't restrict the number of growth points, or if you add branching, that's precisely the DLA picture. So this model is drastic simplification. So we disregard stochastic terms, and then we disregard branching. And the only mechanism we are interested in is the mechanism of competition between branches. Okay.
There's randomness in the initial state.
I'm looking only at stable solutions. So we can extend each arm, and actually this is how pictures are simulated. So, we just do the same as with DLA, so send Brun in motion, and then extend only the arm if the particle hits the tip of it. So it's actually, a little bit stochastic, but that doesn't matter. So we are looking only at stable solutions. All right, so I just mentioned, so if we allow, growth at every point proportionally to a certain power of harmonic measure, then that's, a familiar picture. And the change of parameters eta will give you a more, if eta is bigger, then the arms are more obvious. So eventually they look like. Yeah, these pictures are for DLA. These are for DLA. So forget about branches and watch only at the big.
So you look in your branch growth model.
Ye-
You have a special role played by eta going to 4.
Yes, right. So, I explained that eta is 0 means, no competition. Eta equal to infinity means one clear winner from the very beginning.
So you have the full range.
Full range. And then I want to know so how many arms survive, what are the shapes of the stable configuration. So,
I understand that you don't differential, but do you have any randomness in it except for the starting configuration?
well, that's enough. That's enough for the, when I,
No randomness.
no randomness, a deterministic process. Okay. But randomness in the initial condition, if you want. All right, so let me show you some pictures. And so these pictures, and the work is a joint work with Lennart Carlsson, and the pictures were done at KTH in Sweden by Björn Selander, because our computer skills are very limited. So we start with 3 arms, and then the final shape. So that's every time we rescale to size 1, the final shape is the Mercedes sign almost. Same for the other 2 pictures, right? So every time we end up in the symmetric configuration. For all pictures, eta is 1/2, which is the case of harmonic measure, right? Because the second derivative of conformal map is like square root of harmonic measure. Now, with, say, 7 arms, we observe something. So all 7 arms survive in the first picture, and but it's not clear whether the configuration is symmetric at the end. In the lower experiment, so you see this, one of the arms, disappears. And so eventually we get 6. Then with 8, so we start with the left picture, that's the intermediate state of the process, and the right picture is the final, the stable state. So that's where, everything ends.
This is true in all the pictures so far?
In all pictures, yes, in all.
So in the 3-leg pictures,
Yes.
the third one is not symmetric. Is that?
No, with 3 arms, so
The bottom one is
the bottom one is
doesn't look symmetric.
doesn't look symmetric. I agree. Which is wrong. It should be symmetric. Maybe we need to wait a little bit longer. I had no control over this picture, so otherwise. All right, so with 16 arms, so first every other arm disappears, and then we get this picture, and again, it's not convincing. The arm is bending, one arm is bending, I don't know. All right, so there are several questions.
The initial starting point in this case, those are not equal lengths?
Well, they are almost equal lengths, but with a slight variation, so it's random.
And the angles are not equally spaced?
They were supposed to be a very slight variation of a symmetric configuration. Right, and lengths. And eventually, it doesn't seem to stop. So from the pictures, one can conclude the following. So in most pictures, all arms eventually straighten out. So, and the process tends to a steady state. So second, some arms disappear, and the question is how many arms survive, and if there is a bound for the number of surviving arms. And that's the question I want to address. So our results are basically local. So we are looking at the perturbation of a stationary configuration and work with the Loewner equation to decide whether we get stability or not. Let me now state the results. Okay, yeah. All right. So, can you see this? Yeah. No, this. Don't use it. Yeah. Mm-hmm. Right, so also on these pictures we observe some level of symmetry in the final configuration, and that's also, interesting. So more or less we understand how to do this, except that for more than 3 arms or symmetric configurations, we need we need a computer to get somewhere. But the main tool will be the Wiener-Hopf operator that arises as a result of a linearization of Loewner equation near the equilibrium. So I'm wondering if what would be a corresponding object with a stochastic term, for example. I'll describe what happens when we start with 3 arms. So the answer depends on eta, and then we have several transition values of eta. So the first one, eta 0, is 3. So 6 times, the temperature is 6 times higher than, in the case of the DLA. So the DLA is 1/2. So if eta is greater than 3, then eta naught, then no matter, we can start with, we can have many arms, but eventually the result is very boring. So only, 2 arms straighten out. That's it. Now, the second one,
that's to adopt for generic configuration?
Yeah, that's for generic configuration. Of course, you can have unstable stationary solutions, but then perturb a little bit, and then so we are looking only at stationary solutions of the Loewner equation with the Kalosher-Moser condition. And that's the philosophy. So order to study this, you have some process on the circle, and then you do Loewnerization of this process. SLE is Loewnerization of the Brownian motion. And this simple example is Loewnerization of Kalosher-Moser equations, or Kalosher-Moser system. So the next one is eta 1, which is, there's some explicit number logarithms, so it's about 2.7. And so for eta between these 2 parameters, 1, also everything changes kind of continuously. So what happens, we'll get a small third branch here. And that's the only stable state in this situation. And that's totally asymmetric. So there's no symmetry in this picture.
So that's a stationary?
Yes, right. So for each eta, we have a unique stationary state, which is asymmetric. Somehow we may start with very, very symmetric configuration. Well, I mean, so now at eta 2, which is about 2.1, so these two arms become symmetric. So we have a symmetry with respect to the line of one of the needles. So I call it semi-symmetric. And if eta is less than, well, this eta 2, then nothing changes. So then we have this phase locking. So then everything is tends to, to this Mercedes thing. Yeah, that picture is, well, has to be symmetric. Okay. Now, with
The finals, the asymmetric or not
fully symmetric, right? Somehow, decreasing temperature, you increase symmetry, and that's this is observed in other low-dimensional situations. So you're, I don't know why is it happening, but this is comes from eigenvalues of the from the spectrum of Wiener-Hopf operators. So now. One last thing. So we want also to find a bound for the number of arms in a stable stationary configuration. And one would expect that for any positive eta, only finitely many survive, but certainly the number would depend on eta. We cannot prove that. We can prove this. So if you want, this is theorem 1. And the theorem 2 is that the number of arms in a steady state is less than, well, a certain bound depending on eta, so for eta greater than 1/2. So in the case of harmonic measure, for example, I'm not sure whether, you get some magic number like 7 or 8 or with this. So and the pictures, again, are not very convincing. You get.
Theorem 1 seems to give you the number of arms.
That's only so from here we start with 3. So this is only for 3-arm configuration. The first statement is global. So no matter how you start, if eta is greater than 3, then everything contracts. So that's global attractor. So this is for 3 arms. You start with 3 arms and look at the result. So if you start with many arms, then, it depends on eta. So every time you have, something. So I would like, I don't have enough, evidence from, computational evidence to, give any, to make any, conjecture, which would describe the picture. This looks, I believe, a little bit mysterious how this happens. I think I state the result.